So thank you again, everyone, for coming. As one of the co-organizers of the event, I feel very privileged to be part of this for the last 4 years. And so thank you, Murat and Karl-Heinz, and everyone else who was involved in organizing it. So today, really quickly, I just wanted to go through a few interesting results that we find kind of intriguing from a potential computation impact. It's a little more of a neuroscience story, though. And it relates to a lot of the work you'll hear about tomorrow and Wednesday from some of the other Sandians who'll be speaking. So my interests long-term have been in the hippocampus, area involved in long-term memory, something that might inspire a sort of algorithm that does content-addressable memory. It's the kind of new way of looking at how information can be stored and retrieved in computing systems. And if you look at the hippocampus, it's a very well-understood circuit. I would actually argue that hippocampus people would often say the hippocampus is better understood than the visual cortex in a lot of ways. And the challenge is that we don't have a very clear algorithm that it's inspired. There's been a lot of work in this area, but there's no equivalent of deep learning to the visual cortex in the hippocampus. And so this is a very simple schematic, three-level circuit, and the what I would say from a learning point of view, the hippocampus has to learn, has to acquire information. So people always bring up synaptic learning, STDP, long-term depression, plasticity, and so forth. But in reality, the hippocampus has a lot of other types of learning. It's particularly notable in the hippocampus of most regions. Things like adult neurogenesis, which I've talked about in nice conferences past. Dynamical computation, things like equivalent to like the sort of excitatory inhibitory cortical dynamics people talk about. But also what I'm going to focus on today, neuromodulation. So it's highly regulated by things like acetylcholine and dopamine and serotonin. So neuromodulation in terms of processing sources occurring or learning on very long time scales, relatively long time scales, and very large spatial scales. So this is not a local in terms of, okay, two synapses are coupled and doing STDP. This is a more global effect. And it tends to be very difficult to study. The typical neuromodulatory transmitter often can impact dozens of different sorts of receptors on the downstream, and those receptors have very heterogeneous impacts on the population. So, for instance, serotonin has 7 classes of receptors, and there are a number of subclasses within each of those classes. And the different neurons in the hippocampus, there are dozens of types of neurons, and each of them has a very large distribution of these subclasses of receptors. So it's very difficult to study. But that being said, if you think about things that are more near chaotic in their dynamics, especially when you get to the recurrent circuits like the CA3, what we start to think about is any subtle change to those circuits, a global shift due to something like serotonin, could have a dramatic impact on the computation. So we wanted to look at the effects of modulation on dynamical computation in a more systematic way. So we took basic 80-20 type simulations. These would be done in Neuron and Zeiss, and I have 4 of them up here because it's the same exact network, but it's performed using different solvers. And with the different solvers, and not surprisingly, because of the near chaotic nature of these things, the simulations diverge very quickly as soon as any simulation errors occur. And so in order to get past this, we didn't want to look at modulation and say, oh, it made the network dynamics different. Well, the solver makes the network dynamics different. So we wanted to look at something more under the, kind of beneath the actual spike timings themselves. And so if you look at something like PCA, look at a manifold of the correlational structure of the activity, you see that the correlational structure of these 4 networks is identical. So the principal components of each of these 4 simulations is exactly the same. And that's not all that surprising, given that the correlational structure emerges from the connectivity of the systems. So we went through and we validated this. If you take 2 of the same networks and give them different inputs, the principal components eventually converge. Lower components converge slower than the earlier principal components. Likewise, same inputs, which is kind of artificial, and if you have different networks, eventually fade out. So these are not surprising. Where it gets interesting is if you look at things like probabilistic synapses. If you just add stochastic noise at the synapse, the stuff Paul was talking about earlier, the principal components are the same. It takes a little bit for those components to converge, but because it's kind of white noise added to the computation, the dynamics, the correlational structure of those dynamics is not changing. And the reason correlational structure is important is things like SCDP over the years, people have talked about that ICA and PCA, these sort of correlation finding algorithms, can be emulated by spike timing plasticity rules. So a downstream region of the brain can be listening to an upstream network doing near chaotic-like dynamics and be picking up the dominant components, which are influenced by the inputs and what I'll show is the modulatory state of the system. This is actually quite similar to a liquid state machine in a lot of ways. So we wanted to look at modulation. So instead of taking these more Hodgkin-Huxley dynamical models that I described before, we took a very, very simple leaking, integrate, and fire model with only a couple of parameters like the leaking time constant and the threshold of firing. And we just asked how would just changing these parameters in kind of a global way, kind of adding noise to the parameter as a global perturbation affect those dynamics. And what you see is that we see the same effect, the same network simulated twice, no changes, yield the same principal components even if the dynamics change. So it's valid for the simple model. But if you add something like serotonin, so we modeled serotonin. This is a very, very coarse way of looking at serotonin by just changing the time constants of all the neurons in the network, where you said, okay, instead of every neuron having a 20 millisecond time constant, some of them had 25 milliseconds, some had 22, some had 28, and it's just a global shift of those time constants. Well, not all that surprisingly, but still the effect, the magnitude of the effect was surprising. Any subtle shift of the time constants, the entire correlational structure of the network dissolves. What you end up seeing is that while the first principal component is somewhat slow to break down, everything else just collapses. Now, this is the exact same network, same connectivity structure, same synaptic weights, everything. And so, obviously, the dynamics are important, time constant's important. So what we did next is we looked at what I would call more acetylcholine-like effect. Acetylcholine affects certain interneuron populations in the hippocampus, like parvalbumin cells. Increasing parvalbumin basket cell activity would be like sort of increasing the voltage threshold for everything else to fire. And so it's a very coarse way of modeling it. And you can see that this sort of changing of the threshold is a more gradual effect, but still can be pretty dramatic. So these are kind of the top eigenvectors of one versus the other, and you can see that things have been shifted. It's been fuzzier, but it's not quite as dramatic. So we shift back to this sort of view where neurons are listening to the correlational structure of the networks. And what you can imagine is that while I had a set that looked at the correlational dynamics in a normal one modulatory state, you shift the modulatory state, an entire different population of downstream neurons could become useful. So you could actually have the exact same network trained to process inputs under one state, and you have something to read that out. And then you change the state, but even though the inputs and the network haven't changed, you get a different readout function. So it's a way it's something that we're starting to explore more theoretically and algorithmically of how you may be able to use sort of modulatory state to expand the computational capabilities of a network. So finally, that's it for the technical work, and since I'm the last speaker before lunch, I figured I'd just prime everyone with this. Murat mentioned it earlier that we're looking for people who are interested in working with us on planning next year's conference, and that's something that we'll try to talk about over the lunches. I put tomorrow's lunch as a good time. People can think about it, and then we'll kind of gather tomorrow at lunch and ask, get people's input about what they would like to see in NICE in future years. I like it when conferences do that. We're getting to a point where we have a nice scaling curve. When we first started NICE 3 years ago, we had like 50 people, and the next year was 75. Last year was 100, and now people are sitting in the last row of the balcony. So I think this is great. I really appreciate everyone's interest, and again, thank you to Murat for starting this whole thing. So with that, everyone go eat.